Hi, good evening, everyone. Last time we've talked about the basics of linear programming model with several example problems, right? And we've also learned about the convex sets and the extreme points, right? What is the extreme point? Simply, I would say is the corner point, right? Because for any linear programming model, the physical region will be an convex set, right? And actually the physical region of LP is always a polygon, like this way. And the extreme point of this polygon will be any vertices or the corners, right? So in this class, if I say extreme point, then this means the corner point, okay? And if any LP, any linear programming model has an optimal solution, then it should be one of the extreme points of the physical region, okay? Last time we've also learned that if a solution satisfies all the constraints, then it is called a feasible solution. Otherwise, it is called an infeasible solution, right? So an infeasible solution is a solution for which at least one constraint is violated, right? And the feasible region is the collection of all the feasible solutions, right? And also we've learned about optimal solution and the optimal values of a problem. And last time we've considered this example. And in this case, x1 equals 2/3 and x2 equals 7/15 is the only solution that satisfies all the constraints, right? So it is the optimal solution as well as the feasible solution, right? And the corresponding optimal value would be 2.73. However, for this case, the window glass case, the x1 equals 0 and x2 equals 0 is one of the feasible solutions with the corresponding objective function value g equals 0, right? However, this is not the optimal solution because with different set of x1 and x2 values, for example, x1 equals 0 and x2 equals 4, we could obtain another feasible solution, right? And it provides even better objective function value, which is g equals 20. However, we are still not sure if this is the optimal solution, right? And today, we are going to learn about graphical method, which can find the optimal solution for this window glass problem so easily. And I just let you know that any LP problem, any linear programming problem with only 2 decision variables can be solved graphical method, okay? Can be solved by graphical method. And the procedure involves the constructing a 2-dimensional graph with x1 and x2 as the axis, right? And the first step is to identify the values of x1 and x2 that are permitted by the restrictions. And this is done by drawing each line that borders the range of permissible values for one restriction. So first, the non-negativity restrictions, x1 is greater than equals 0 and x2 is greater than equals 0, requires both x1 and x2 to lie on the positive side of the axis, right? So is that the first quadrant, right? And the next restriction, which is x1 is less than equals 4, means that x1, x2 cannot lie to the right side of the line x1 equals 4, right? Likewise, the restriction 2x2 is less than equals 12 implies the line 2x2 is less than equals 12 should be added to the boundary of the permissible region, right? And another restriction, 3x1 plus 2x2 is less than equals 18 is added to complete the boundary of the feasible region. That is just, if we use x1 equals 0 and x2 equals 0 into this constraint to check if it satisfies the constraint 3x1 plus 2x2 is less than equals 18, then the left-hand side with x1 equals 0 and x2 equals 0, the left-hand side becomes 0, right? So 0 is less than equals 18, so this constraint is satisfied. And because the point 0 does satisfy 3x1 plus 2x2 is less than equals 18, we may conclude that the 0, 0 here is one of the feasible point, right, based on this line. So the feasible region would be the point below this line, right, which is this side, and the line itself. So the resulting region of permissible values of x1, x2 is called a feasible region in this case. And I want you to record your memory. So how many extreme points do you have in this case? 5, right? Because we have only 5 corner points in this feasible region, right? So we have only 5 corner points, extreme points, like this way. So the next is, because we already identified the feasible region for this window glass problem, now we search for the optimal solution, which will be the point, the feasible region, with the largest value of z equals 3x1 plus 5x2. And to find the optimal solution, we need to graph a line on which all the points have the same z value, okay? And in the maximization problem, this line is called an isoprofit line, and the minimization problem, it is called an iso-cost line, right? But in general, such a line is called an iso-value line, okay? So to draw an iso-value line, you need to choose any point in the feasible region and calculate its z value, the objective function value, okay? So, for example, let's choose point 0.04, okay? And for the point 0.04, the corresponding z value is going to be 20, right? Because 3 times 0 plus 5 times 4 becomes 20. So the 0.4 lies on the iso-value line, which is z equals 3x1 plus 5x2 equals 20. Right? (3x1 plus 5x2 equals 20). So this can be rewritten as x2 equals minus 3 over 5 x1 plus 4, right? So which means this line has a slope of negative 3/5 and x2 intercept 4, right? And all the iso value line have the same slope because all the iso value lines of the form of 3x1 plus 5x2 equals any constant values, right? Which means that once we have drawn one isovalue line, we can find all other isovalue line by moving parallel to the isovalue line we have drawn. So in this problem, the objective function value g will decrease if we move in a direction for which both x1 and x2 decreases, right? So we construct another isovalue line by moving parallel to 3x1 plus 5x2 equals 10 in a southwest direction, right? Likewise, the objective function g will increase if we move in a direction for which both x1 and x2 increase. So we can construct another isovalue line by moving parallel to this line in the northeast direction, right? And now we know the optimal value of 36 for this problem would be found with the isovalue line touching the, what is that? The feasible region, touching the feasible region, okay? So once the optimal solution to an LP has been found, it is very useful to classify each constraint as being a binding constraint or a non-binding constraint. Let me just read what they written down in the screen. A constraint is binding if the left hand side and the right hand side of the constraints are equal, when the optimal value of the decision variables are substituted into the constraint. And the constraint is non-binding if the left hand side and the right hand side of the constraints are unequal, when the optimal value of the decision variables are substituted into the constraint, right? So graphically, it is easy to see which constraint is binding and non-binding. So for this optimal point, this constraint is non-binding, right? x1 is less than or equals 4. This constraint is non-binding constraint. That is, if there is a gap between the line and the optimal point, then the corresponding constraint is non-binding constraint, okay? Which means the following, these two lines, these two constraints are the binding constraints, because there is no gap between these lines and the optimal point, right? So in this case, we have two binding constraints based on the optimal point, right? So actually, in that case, the optimal point occurs in the intersection of two binding constraints, right? So if we solve these two equations, like 2x2 equals 12 and 3x1 plus 2x2 equals 18. And from this, x2 equals 6. And if this is 6, then x1 becomes 2, right? So if we use these two values, then our objective function value would be g equals 3 times x1 times plus 5 times x2. x1 is 2, x2 is 6. So the maximum profit would be $36,000, for example. Okay? It's very easy, right? Then let's consider another very simple example like this. Let's try to find the optimal solution for this problem using the graphical method. Okay? Here, the shaded area is the feasible region. Okay? And again, we have only 5 extreme points, right? So if this problem has the optimal solution, it should be one of these extreme points, right? So to find the optimal solution, we need to grab an iso value line first, right? And I said to draw an iso value line, you need to choose any point in the feasible region and calculate the corresponding the objective function value, which is g value, right? So if I choose 0, 1, for example, then the corresponding g value is going to be negative 2 times g 0 minus 1, right? Which is negative 1. Which means this point 0, 1 lies on the iso value line g equals negative 1, right? So if you look at this screen, like I said, the point 0, 1 lies on the iso value line, negative 2x minus y equals negative 1. And by moving parallel to the iso value line, we have drawn in the northeast direction. We could improve the value of g, which is negative 2 in this case. Okay? And by moving parallel to the iso value line in a northwest direction again, we could improve the value of g, which is negative 4. Okay? Because our objective function, our objective is to minimize negative 2x minus y if we have the smaller value, which means our objective function value has been improved. Okay? And again, by moving parallel to the iso value line in the northwest direction, we could improve value of g, which is negative 5 in this case. And this is the last iso value line intersecting the feasible region, right? Which means after this point, the iso value line will no longer intersect the feasible region. So we may conclude that the optimal solution has been found with g equals negative 5, with x1 equals 2 and r is x, right? Just x equals 2 and y equals 1, right? Then let me just ask you at this point, which constraint is binding if you consider the optimal point, which is this. We have two binding constraints, which is this and this, right? And this constraint is non-binding constraint because there is a gap between this line and this optimal point, right? Is that correct? And this slide shows the required steps of graphical method for any linear programming model. Okay? So first of all, you need to identify the feasible region, and then plot an iso value line corresponding to a feasible solution, and move this line in improving direction and find the last isovalue line which intersecting the feasible region. Okay? And any points on the intersection of the last isovalue line in the feasible regions are the optimal solution for the given problem. Okay? Okay, then let's consider another example. Let's try to find which point is optimal. Okay? And now we are given with the feasible region like this. Again, we have 5 extreme points. Right. So if there is an optimal solution, then one of them should be the optimal solution, right? So first of all, we need to draw an isovalue line, right? So let's just choose any point in the feasible region, right? And how about if I choose point, let's say 1, 0, okay? Something like this, maybe 1, 0. So with this value, x1 equals 1 and x2 equals 0, our objective function value would be 3 times 1 minus 0 becomes 3, right? Which means 3x1 minus x2 equals 3, and x2 equals 3x1 minus 3, right? So this line has the slope of 3 and x2 intercept of negative 3, right? So it's going to be something like this. Okay? Let's say this is negative 3 and the slope is 3, right? So this is the isovalue line that I've chosen. And you remember, all the isovalue lines has the same slope because it has the form that 3x1 minus x2 equals some constant, right? And then in this case, the objective function value, g, which is z here, will be improved, which means the g value will be decreased if we move isovalue line in a direction for which x1 is decreased and x2 is increased. Is that right? So if we move this isovalue line with the direction that x1 is decreased and x2 is increased. So in a northwest direction, right? So you need to move this isovalue line to this direction to improve the objective function value, right? Then, of course, it's obvious our optimal solution can be found with this point, right? Because at this time, the isovalue line intersect the feasible region, okay? How about next example? So which point is the optimal? Does anybody want to guess? So for this example, let's choose 0.03, just for example. Okay. So x1 equals 0 and x2 equals 3. We have g values negative 2 times 0 minus 3, which is negative 3, right? Which means this point 0.03 lies on the isovalue line, which is g equals negative 2x1 minus x2 equals negative 3. And this can be rewritten as x2 equals negative 2x1 plus 3, right? So this line has negative 2 as the slope, and y1, I'm sorry, the x2 intercept of 3, right? So it's like something like this. Isovalue line will be like this, right? And in this case, our objective function value will be improved, will be decreased, right? This is the minimization problem. So our objective function value will be decreased if we move this isovalue line in a direction for which both x1 and x2 is increased, right? So if x1 is increased and x2 is increased, like this way, so we need to move this isovalue line this direction, right? North-east direction. And I believe the optimal point would be this, okay? So it looks like parallel, but it is not, okay? This is not a parallel line. This line has a deeper slope than this, okay? So this should be the optimal point in our case. What about the third case? At this time, we are dealing with maximization problem rather than minimization problem, okay? And let's choose 0.11, for example. So with 0.11, which is x1 equals 1 and x2 equals 1, we will have g values would be 2, right? Which means this 0.11 will be on line x1 plus x2 equals 2, right? Which will be x2 equals negative x1 plus 2. So the line has negative 1 as the slope and x2 intercept of 2, right? So it's like this, okay? So if we move this isovalue line in a direction for which both x1 is increased and x2 is increased, then this g value will be increased, right? Which means we need to move the isovalue line in this direction, okay? Because in that way, the x1 value will be increased, likewise x2 value will be increased, right? However, in this case, one of the constraints, which is this constraint, has the same slope as our isovalue line, right? In our case, isovalue line has slope of -1, and this one, this constraint, will be like this, -x1 plus 6. It also has -1 as the slope, which means these two lines are parallel. Okay? What does it mean? Not just two, right? Infinite number of points, right? Infinite number of optimal solutions we have, which means every point between these 2 points, right, will be the optimal solution, right? In that case, the dark line segments between these 2 points, 2, 4, and 4, 2. So the optimal solution for our case, right? So in this case, we may say that this problem has infinite number of optimal solutions. Okay? Okay, so far we've learned about the graphical approach for LP, linear programming problem, right? And we've learned that the graphical method works very well for LP with only 2 decision variables, okay? Actually, it could be used for 3 decision variables case, but it will be very complicated, okay? Because you need to deal with 3 dimensions instead of 2 dimensions, right? But still, it does work for 3 decision variable case. And actually, it's impossible for the case with 4 and more decision variable case, right? However, at least the graphical method is very good to illustrate the concepts and aid in conceptual understanding and so on, okay? Okay, now we are going to talk about 3 types of linear programming problems that does not have unique optimal solution, okay? As it says, whenever a linear programming problem has an optimal solution, it has a corner. There is always an optimal solution on one of the corners of the feasible region, right? However, it doesn't mean that the linear programming problem always has an optimal solution. Also, it does not say that all the optimal solutions have to be on the corners, okay? What are the possibilities that a linear programming problem does not have an optimal solution at a corner point? There is, in this case, for example, there is no real values that is simultaneously less than the value of -1 and greater than the value of 0, right? So in this case, the feasible region is empty, which means feasible region contains no points, right? Resulting in an infeasible linear programming problem. Because the optimal solution to an LP is the best point in the feasible region, an infeasible linear programming problem has no optimal solution, okay? And this shows a general case of infeasible linear programming problems. Because there is no feasible region which simultaneously satisfies these 2 constraints in this case. So feasible region is empty in this case. And this results in an infeasible linear programming problem. Okay? The next is we call unboundedness case. So when the graphically solving an LP, we can spot an unbounded LPs. Okay? Like this example, this is the maximization problem, right? When we move parallel to our original isoprofit line, isovalue line, in the direction of increasing G value, we never entirely leave the feasible region. Okay? Because if we move isovalue line, which is this line, in this direction, we can improve our objective function value. But we never leave our feasible region. Okay? This is the case of unboundedness or unbounded LPs. Okay? And this shows a general case of unbounded LPs. Okay? Of course, likewise, a minimization problem could be unbounded below. If we never leave the feasible region, we're moving in the direction of decreasing our objective function value, G. Okay? This is the same. Then what other possibilities that we could have other than the unique optimal solution case? This is the case that we've seen with an example, right? I said this about the infinite number of optimal solution case. So for example, in this case, one of the constraints has the same slope as the isovalue line, right? In that case, all the points between this dark line segment between the 2,4 and 4,2, so they are going to be the optimal solution, optimal point, right? So every point between these 2 points is going to be the optimal solution. And this shows a general case of multiple or infinite number of optimal case. Okay, then in summary, we can see that every LP must fall into one of them, one of the following 4 cases. Okay, the first case is LP has a unique optimal solution. Second case would be the LP has an alternate or the multiple or infinite number of optimal solutions. So in that case, 2 or more extreme points are the optimal, and the LP, the linear programming problem, will have an infinite number of optimal solutions. The next case would be an infeasible case. In that case, the feasible region contains no points, right? And the last case is about the unbounded LP. So in this case, there are points in the feasible region with arbitrarily large G value, of course in a maximization problem, or arbitrarily small G values in the minimization problems. Okay, so is there any questions so far about graphical method? It's pretty easy, right, to use. Okay, then let's talk about LINDO and LINGO, which is the optimization solver package with this small example problem. Let's call this chicken feed problem. So in this example, a farm manufactures chicken feed by mixing 3 different ingredients. Okay, and each ingredient contains 4 key nutrients, which is protein, fat, and vitamin A and vitamin B. Okay? And the amount of each nutrient contained in 1 kilogram of 3 basic ingredients are given in this table. And also the cost per each kilogram of ingredients, 1, 2, 3 are 55 cents, 42 cents, and 38 cents respectively. And you could find those values within this table too, right? And also this table shows each kilogram of the feed must contain at least 35 grams of protein, and a minimum of 8 grams and maximum of 10 grams of fat, and at least 180 units of vitamin A, and at least 9 units of vitamin B. And we are required to formulate a linear programming problem to find the feed mix that has the minimum cost per kilograms. Okay? So first of all, you need to set up the decision variable, right? So how do you set up the decision variable for this case? How many decision variables do we need? 3, right? So let's say x1 represents the kilogram of ingredient number 1 included in mixture, okay? And x2 is the kilogram of ingredient number 2, and x3 would be ingredient number 3 included in mixture, okay? And what is our objective function? Minimize the total required cost, right? So I would say minimize sum over I is going to be 1, 2, 3, and C sub I times X sub I, right? Of course, C sub I is the cost per kilogram of ingredient number I. Okay. So our actual objective function would be, looks like this, 0.55 times x1 plus 0.42 times x2, right? Plus 0.38 times x3. This is our objective function, right? It's straightforward. What constraint do we need to consider? First of all, each kilogram of the feed must contain at least 35 grams of protein, right? So let's say constraint each kilogram of the feed must contain at least 35 grams of protein, right? Can be expressed by 25 x1 plus 45 x2 32 x3 is greater than or equals 35, right? Because it should contain at least 35 grams, right? And next constraint would be about fat. So each kilogram of fat must contain a minimum of 8 grams, a maximum of 10 grams, right, of fat. So each kilogram of feed must contain a minimum of 8 grams and maximum of 10 grams of fat. Okay. So it's going to be 11 times x1, 10 times x2, 7 times x3. Is greater than equals 8, but we need another constraint. Same left-hand side, that should be less than equals 10, right? It's pretty easy. And the next would be about vitamin A and vitamin B. So each kilogram of feed must contain at least 180 units of vitamin A. Okay. So it's going to be 235 x1 plus 160 x2, 190 x3 is greater than equals 180. Next constraint is about vitamin B. So each kilogram of feed must contain at least 9 units of vitamin B. Okay? Which is 16x1 plus 6x2, 10x3 is greater than equals 9, right? And another constraint that you need to consider is the total weight of the mixture should be 1 kilogram, right? That is, the summation of x1 and x2 and x3 should be equal to 1, right? Because, as I said, total weight of mixture should be 1 kilogram. Okay? And the last restriction would be the sign restriction, right? Because each ingredient included in the mixture cannot be negative, right? So each variable, x1 is greater than equals 0, x2 is greater than equals 0, and x3 is greater than equals 0, okay? So if you combine all of this, including objective function and constraint sets, including the sign restriction, then the complete LP for this chicken feed problem looks like this, okay? please look at the second handout. Okay. And this is the actual input for LINDO program, which is one of the most popular optimization solver. It's very easy to handle. So I assume many of you are familiar with LINDO, right? No? Okay. But don't worry. Let me just briefly show how you could use it. Okay. So basically, LINDO assumes that all the decision variables are non-negative. Okay, which means the non-negativity restrictions are unnecessary for LINDO input. Okay, you could include that, but it's just time-consuming. Okay, and okay here. And for the first requirement, the objective, you have two choices, right? Either max or min, right? Which stands for maximize and minimize, right? The first word in the LINDO model must be either max or min, okay? The formula you enter after the max or min is called the objective function, LINDO. And on the next line of the objective function, you need to enter the word subject to, or just the letters ST, okay? And then on the next line of your model, you just need to enter each constraint one by one, okay? And just remember, all of the decision variables should be located in the left-hand side, okay? Which means every constant should be in the right-hand side, okay? And another thing I should let you know is LINDO does not need asterisk as the symbol of multiplication, okay? And on the line after that, we designate the end of the constraints by adding the end mark, END, okay? And right after an exclamation mark, you could enter any comments to improve the readability of the model, okay? And once the LINDO model has been entered into the LINDO model window, the model can be solved by clicking the Solve button on the toolbar, okay? Okay, this is the LINDO output for the chicken feed problem. According to this result, the minimum mixture cost is $0.398 per kilogram and consists of 0.045 kilogram of ingredient number 1 and 0.273 kilogram of ingredient number 2 and 0.682 kilogram ingredient number 3, okay? And the reduced cost for any variable that is included in the optimal solution is always 0. And for the variable not included in the optimal solution, the reduced cost shows how much the values of the objective function will be increased for a minimization problem, or will be decreased for a maximization problem. If 1 unit of that variable were to be included in the optimal solution. I'm going to talk about this reduced cost and yield prices later on when you deal with sensitivity analysis, so don't worry about it at this moment. And of course, the slack or surplus column in the solution report shows how the tight constraint is, right? Not here. Here, okay. So if a constraint is completely satisfied as an equality, then the slack or surplus has the value of 0, which means the corresponding constraint is binding, okay, based on the optimal point. If the slack or surplus has any positive value, then this tells you how many more units of the variable could be added to the optimal solution before the constraint becomes an equality. Okay? And as I said, both the reduced cost and dual prices would be very important, but I'm going to talk about that when you consider the sensitivity analysis later on. And this is another part of LINDO output. Like reduced cost and dual prices, we're going to talk about all of this information later when we deal with sensitivity analysis. Okay? Okay, then this is the input for LINGO, which is another popular optimization solver. And the format for the input of LINGO is slightly different from the one in LINDO. So basically, a LINGO model starts with the word model and column, and then end with end mark. Okay? And unlike LINDO, the LINGO does not recognize the word minimize or maximize. Okay? So you have only two choices, max or min, for LINGO, which stands for, of course, maximize and minimize. Okay? And right after the word min or max, equal sign is required. Okay? And unlike LINDO, the next line of the objective function, we don't need the word subject to nor the letter st. Okay? That's the major differences between LINDO and LINGO. And each mathematical expression in LINGO is terminated with a semicolon. Okay? Which means LINGO cannot solve the model without this semicolon. Okay? And then expression may be broken up into as many lines as you want, but the expression must be terminated with a semicolon again. Okay? So just as an example, we could have used 2 lines rather than just 1 to contain the objective function like this. Because we didn't have any semicolon at the end of this x2 variable, LINGO just assume this is just 1 line, not the 2 lines. Okay? And likewise, LINDO, we have also entered some comments to improve the readability of the model. And comments begins with an exclamation point, exclamation mark, and again end with a semicolon. So all the text between an exclamation mark and the terminating semicolon is ignored by LINGO. Okay? And as you can see here, the comments can occupy more than 1 line and can share lines with other LINGO expressions, just like this. And likewise, LINDO. LINDO is not case sensitive. Okay? That is, both LINDO and LINGO does not distinguish between uppercase and lowercase in variable names. So all these 4 variable names would be considered equivalent in both LINDO and LINGO. Okay? And another feature you will notice is that the LINGO's editor is syntax aware, they said. In other words, when it encounters LINGO keywords, it displays in blue color, okay? And comments are displayed in green color, and all other remaining text is displayed in black. So you should find this feature very useful in tracking down any syntax errors in your model later on. Okay? And like LINDO, once the LINGO model has been entered into the LINGO model window, just you need to click the solve button on the toolbar. Then LINGO will solve the problem automatically. Okay? Okay, this is the all for today, and I will see you next time. Thank you very much.